Welcome to this first joint series of Interreg guest lectures. Our first guest speaker today is Professor Joris Thibaut from Ghent University. Joris is Senior Full Professor in Catalytic Reaction Engineering at the Laboratory for Chemical Technology. He is heading the Catalytic Reaction Engineering Research Group, comprising about 15 junior researchers. They actively investigate a variety of large-scale industrial reactions and more particularly the rational design of the corresponding catalysts as well as of the reactors in which these catalysts are employed. In 2014, he received a prestigious ERC Consolidator grant for model-based catalyst design for the conversion of renewables into chemicals and fuels. Joris is also coordinator of Ecoduct, a Horizon Europe project in the framework of electrified catalytic reactors. He will introduce you to the OBIWAN project, of which he is the coordinator, and give a guest lecture on catalytic reaction and reactor engineering for biogas valorization. Joris, the floor is yours.
Okay, thank you, Elisabeth, for the nice introduction, and thanks to all of you for being here and taking part in these guest lectures. As Elisabeth said, I will first give a short introduction to the OBIWAN project. That will be about 10 to 15 minutes, and that will then be followed by a more detailed presentation on the actual part that I'm doing, I'm coaching within the OBIWAN project, which is indeed effectively the reaction and reactor engineering for biogas valorization. So, but first, the OBIWAN project by itself. As you can imagine from the title, well, also of my talk and of what the acronym OBIWAN stands for, OBIWAN is situated in the area of biogas production on the one hand and valorization on the other hand. Now, biogas as such is a gas that mainly consists of methane on the one hand and carbon dioxide on the other hand, and it is produced by having typically organic waste by bringing it in an oxygen deficient environment such that bacteria can do their work and convert the larger entities, the larger molecules into smaller molecules, and the two end products are, well, as indicated over here, the two major end products are methane, the reduced version of carbon, you could say, and CO2, the oxidized version of carbon dioxide. Quite peculiar for biogas is that one of the routes from which it can be made is via the sludge of wastewater treatments. And in contrast to many other bio-related feedstocks from which the availability decreases with the population density, the availability of biogas, definitely the biogas originating from the sludge of wastewater treatment plants, that availability increases in densely populated areas. And that is why the north of France, Walloon, Flanders area is in fact a quite ideal area for the OBIWAN project and for biogas generation, and then ultimately the upgradation of the biogas. So far, well, you can effectively see from this figure that biogas there is a quite pronounced production of biogas. We are not ahead of Europe. Ahead of Europe is Germany with the largest installed capacity per capita. However, well, we are definitely not doing bad. If you, as you could see from this plot also over here. In absolute numbers, so Germany is not only doing well in terms of relative numbers, but also in terms of absolute numbers, it is having the highest installed capacity, followed by Italy. But per million capita, and also because of some time difference in here, the relative the relative density of biogas plants is a little less pronounced in Italy. And France and Belgium are situated a bit further down the road, but well, we can clearly see from the figure that we have over here that biogas production is definitely also picking up in our region. So looking for opportunities to do something with it is definitely quite welcome. Another measure is related to the number of biogas plants and the corresponding installed electric capacity. And you can see over the years how this has been growing. And with current evolutions, the presence and availability of own gas, biogas, is of a definite strategic advantage. If we zoom out more globally, well, we see from these figures that Germany was the front runner in Europe, but Europe as a whole is the global front runner, with about half of the global biogas production occurring in Europe, which in fact also underscores the statement of the biogas availability, that it can effectively increase with the population density. Some numbers further. In the year 2023, the total biogas production was globally was about 444 billion cubic meters, and in Europe that was about 22. So Europe underscoring indeed that Europe stands for about half of the biogas, the global biogas production. Some further numbers underlining the increase in the various regions, but particularly in Europe, whether it is biogas or biomethane. Biomethane is then the gas produced from biogas after separating out the carbon dioxide, which then typically is done using membrane purposes, resulting in biomethane, which can even be injected in the natural gas grid as it is used as of today to distribute natural gas on the private market for heating homes, for example. Biogas can effectively also be upgraded to that kind of quality in order to be used on a commercial and a private label. But is calorific valorization really the only possibility? Well, that is not what we believe in as part of the OBIWAN project, and we consider it a downside or a minimal use of biogas if we would essentially just use it for calorific purposes. So why not, in the present context of shortage of fossil resources, difficulties in trading it, in getting it where it is needed, why not trying to provide us with our own feedstocks in order to produce fuels and chemicals as we need? That is what we are exploring, what we started exploring in the OBIWAN project, which is now running for a little more than a year. So the first aspect on which one of our partners, and the partners themselves will get introduced later on, are focusing on is effectively the biogas production. How can we better understand the biogas production? What are the factors determining the selectivity, the yield, the reaction rate? Such kind of things are all important to know in order to be able to design biogas plants properly. Of course, the gas coming out, if we want to do something with it, it will need to be purified and potentially, it will also require separation in order to have more concentrated streams. So the purification, that refers to contaminants such as sulfur, H2S can be present to a certain extent in biogas. That is one of the main constituents which is being investigated in terms of purification. In terms of separation, it is effectively a matter of removing the carbon dioxide from the methane in order to further process them separately. And one work package or one specific task within OBIWAN will further look at the processing of the methane, more particularly its pyrolysis. That means splitting the methane into hydrogen and solid carbon. And this is a hydrogen production technology which does not inherently generate CO2 emissions, which is quite unique compared to other methods to produce hydrogen. So that is a major advantage, rather than having the solid leaving the system as CO2 and typically being vented into the atmosphere. The carbon is now leaving the equipment, leaving the installation as solid carbon, which has certain applications, maybe not that many yet, but still, even if there would not be a direct application, the fact that the carbon is obtained in its solid form means that it is not leading to CO2 emissions. The hydrogen in the proposed OBIWAN concept is then used to hydrogenate the carbon dioxide, which has been separated from the biogas, and that results in methanol. But apart from methanol, together with the methanol, there will also be an equivalent of water produced here, which of course has no further use as a chemical. And uses for methanol are, for example, to make sustainable aviation fuels via methanol to olefins and further oligomerization. Methanol is also a platform chemical for the production of chemicals. And solid carbon, as I referred to, can be used as a filler in car tires or all other kinds of tires, and is also used as a material for gas cleaning. And in the end, definitely after use of fuels, the carbon will end up as carbon dioxide, which can be taken up again by the biomass, which is ending up as the waste biomass in the biogas digesters. So in that sense, we can claim that the OBIWAN loop is getting closed. If it is not in a single season, then during several seasons where the carbon uptake by the plants is occurring. So with OBIWAN, our aim is to reduce greenhouse gas emissions, on the one hand, by effectively avoiding emissions, so by not generating carbon dioxide, and by transforming gases into valuable products. And with this, we focus on Interreg priorities, such as the transition towards a circular economy, the development of innovative technologies to support adaptations to climate change, decrease of pollution on land, in air and water, and also waste recycling. So the OBIWAN innovations are related to the stable production of biogas, also the demonstration of hydrogen production at an industrially relevant scale. And with the technique, we have chosen the methane pyrolysis or the catalytic methane decomposition into solid carbon that corresponds to the so-called turquoise type of hydrogen. And apart from those two, there is, of course, also innovation in relation to purification and separation of biogas and into the CO2 hydrogenation towards methanol. We're not doing this alone at Ghent University. We have three more partners, namely the University of La Salle, which is combined in the Université de Technologie Compiègne and the Sorbonne Alliance University. This is a partner from the region of the north of France. Then there is also Certec from Wallonie, who is focusing on the purification and the separation. Uni La Salle is focusing on the biogas production. Then there is CNRS, one of the CNRS labs, but that one particularly in Lille on catalysis, focusing on CO2 hydrogenation. And within Ghent University, we are focusing on the hydrogen production via the methane pyrolysis. And in order not to only show figures, but also some faces of who are doing the work, not to start with myself, I will start bottom up. So from CNRS, the lead PI is Andrei Kodakov, working on the CO2 hydrogenation to methanol, which is one of the tasks within work package 4. From Certec, we have Benoit Carteuser as PI focusing on the purification and the separation in work package 3. Then there is Xiaoyang Liu from Université La Salle, focusing on the biogas production. And then there is ourselves, Elisabeth and myself. So Elisabeth is the project manager, mainly responsible for work packages 1 and 2. And then myself, I'm acting as the project coordinator, but also active within work package 4 on the methane pyrolysis, on which I will bring the next lecture, the next presentation, which is our guest lecture. Okay, fine. So I will continue with the first guest lecture, which is on catalytic reaction and reactor engineering for biogas valorization. Well, as first slide, I don't think I need to explain a lot further here, but the biogas is mainly composed out of methane and carbon dioxide. As of today, as you can see, it is mainly used for its calorific value. Hence, what if we could transform it into chemicals? Would that not make it worth more? Would that not increase the value of biomass and also provide a strategic advantage? Because biogas, as I have explained, can be produced locally, even in relatively densely populated areas. So it can provide us with some independence from supply of fossil resources, otherwise fossil resources. But of course, in order to convert the biogas into chemicals, we will need reactions, certain reactions that need to occur, and reactors in which those reactions will need to be performed. And there is a played of reactions available, both for methane as well as for carbon dioxide. For methane, in order to make hydrogen or to valorize it, otherwise than simply burning it, one can perform steam reforming in order to produce hydrogen and carbon monoxide, so-called synthesis gas mixture. Sometimes the focus is on the hydrogen production, and then the carbon monoxide will be used to even further reform via water gas shift, even produce some hydrogen more, but it will also enhance the CO2 emissions in relation to hydrogen production via steam reforming. The pyrolysis is the catalytic methane decomposition, where the carbon is ending up as solid carbon next to the hydrogen. And another route in order to valorize methane is oxidative coupling of methane. This is an exothermic reaction, releasing energy, also coming with its own challenges. CO2, despite being a highly stable molecule, is also a molecule which can be valorized via various reaction pathways. Dry reforming is an option, hydrogenation is an option, the reverse boudoir reaction with solid carbon is an option. When it comes to reactors, many reactions are either exothermic or endothermic, and exothermicity is typically dealt with by performing the reaction in a multitubular type of reactor or by making use of a fluidized bed in order to be able to get rid of the heat quite easily. In case of endothermic reactions, the challenge is to get the heat where it needs to be in the reactor. And this can be done by, or is right now mainly done by making use of fired furnaces. But electrification there also provides opportunities to bring the heat where it should be used. And within the OBIWAN project and within the Ghent University activities of the OBIWAN project, the focus is on pyrolysis on the one hand as a reaction, on electrification on the other hand, and on the side of the reactor. Of course, hydrogenation of CO2 is also relevant within the OBIWAN project, and it is being performed by the group of Professor Kodakov at Lille, at CNRS in Lille, but that will not be the topic of today's lecture. So, after this introduction, well, there are the clear two parts. The first one on the reaction engineering, and there I will give some explanations on hydrogen production and why we choose for methane pyrolysis, which is a reaction that has important gas phase contributions, but where the reaction is ignited, one could say, which is initiated by surface reactions. And a reaction can, of course, not occur just by itself. It needs to be contained in a reactor to occur safely and efficiently. And in the present case, we have chosen for an electrified reactor, more particularly an electrothermal fluidized bed type of reactor, which is quite novel and for which we have also constructed a corresponding model. So, but first, the part on the catalytic reaction engineering and the choice of the reaction with some further explanation. So for the conversion of methane and more particularly the production of hydrogen, typically from methane, these are the various options as they are typically employed today. What we can mainly see is that if we focus on steam reforming, coal gasification, and electrolysis, that is the corresponding CO2 emissions that are equivalent with it, or the corresponding cost of the hydrogen, which is becoming excessive when recurring to a technology such as electrolysis. This is why catalytic methane decomposition or methane pyrolysis is coming into the picture. Its heat effect is more moderate as compared to the heat effects of the other possible technologies, be it endothermic or exothermic. And by the reaction by itself, no carbon dioxide will be produced, will be released. So we have the possibility to, or we have the perspective to have a CO2-free hydrogen generation process. Moreover, the catalyst that can be used for it can be carbon-based. So the catalyst is not an expensive noble metal type of catalyst. It is a cheap material, of course, a material from which we want to understand the performance properly. Because the reaction is also referred to as pyrolysis, it is clear that it also relies on the occurrence of gas phase reactions. And those gas phase reactions, when we will later model the reaction, we will do that making use of a reported Aramco mechanism. And that is something which we have considered as carved in stone. The gas phase reaction mechanism was not further adjusted as part of the work. But crucial in order to have the reaction occurring at relevant operating conditions and relevant temperatures and not too extremely high temperatures is the presence of a catalyst. There are metals, and more particularly nickel-based catalysts that are present and that are working for catalytic methane decomposition. They as such are working good, but inherent coke formation on those catalysts is one of the issues which can be resolved, which can be mitigated by recurring to carbon-based material as the catalyst. And that is what we do within the OBIWAN project. And the carbon structure is drawn here as a graphitic structure. And quite important to realize here is that depending on the position of the ending hydrogen atoms, the surface hydrogen atoms, we make a difference between zigzag hydrogen atoms, zigzag active sites, and armchair active sites. We're not the first to investigate this reaction. More than 15 years ago, Lacroix et al. From Nancy has been investigating this reaction already quite in detail. These authors devised a surface reaction mechanism containing 66 species and 275 reactions. But it was not necessarily used for the specific carbon material that we are using. And also Lacroix made his model more or not specifically for methane, but started from propane as one of the reactants. In the model, given the surface reactions that are there, certain of the model parameters that we used, we will label them as catalyst descriptors because they will account for the impact of the catalyst on the reaction. More particularly, so I have drawn the carbon here in a quite idealized graphitic structure. Real carbon materials will not necessarily have such an idealized structure, and different types of catalysts, of carbon catalysts, may have different kinds of layers, and hence that may lead to different amounts on the one hand of zigzag sites and armchair sites, but the exact structure may also impact the reactivity, the way those sites interact with the components. Carbon materials, how do we make them? How can we tune them? Well, it's not my purpose to dwell a lot on that, but this is mainly work by Simon, one of our PhD students, also working within the framework of the ETFB reactor. And this is some of his first work in which the carbon catalysts have been made by a templating method. So first, the inverse is being made in silica, which is then filled with a polymer, which is then getting carbonized. And after etching away the original template, we are left with a carbonaceous material. So in this manner, we can tune the active sites on the catalyst. Well, as you can see from the timing of those two publications, this is work that has essentially been done in parallel. So Surush, one of our other collaborators, one of our postdoctoral collaborators on the project, has been working on other data during the same time. In order to making use of some literature reported data on different kinds of carbon black with different numbers of active sites, different numbers of active site density, and mainly a difference in surface area, to determine the catalyst descriptors that allow explaining the differences in the behavior. And from the large number of surface species and surface reactions, we have selected the surface reactions that are listed over here as the ones from which we allowed the parameters to be readjusted compared to the values that have been reported before. And what do these reactions stand for? So, well, we have here a carbon which is in the surface, hydrogen which is also attached to the surface, and in this case it is on an armchair site. In this case here, the Z refers to a zigzag site. And in the presence of a hydrogen atom, or in the presence of a hydrogen radical, better, This hydrogen will be abstracted. It will give rise to a hydrogen atom in the gas phase and a empty active site, a generated active site on the carbon. And the carbon, because it is now empty, it has emerged to the surface. That is why the S is here, whereas the B for the bulk remains over here. Well, and I will not go through all of these reactions, but those are the crucial ones, which are explaining the initiation, and particularly the reactions 5 are explaining the decomposition of the original active sites, both on the armchair and the zigzag. And these were the original values, and here are the ones as we needed to readjust them in order to make the model as originally devised by Lacroix to make it fit to our data and the data for methane pyrolysis. So one of the main differences in the results obtained for the different catalysts, either making use of the model and the parameters as reported by Lacroix and by our own work, well, we see that there is a significant difference simulated between the number of free active sites, be it the armchair sites or be it the zigzag sites. And the main difference, on the one hand, was having essentially two reasons. So the first reason was that on the one hand, methane by itself is more difficult to activate than propane. Propane is having a secondary carbon atom where the hydrogen carbon bonds are slightly weaker than in methane. Hence, the dissociation of the dissociation of propane into a propyl radical and a hydrogen radical is easier to occur spontaneously. And so that is essentially the first reason, and a consequence of that first reason is then the second reason, because of the ease of the initiation by a propane molecule in the gas phase, the potential initiation by the reaction on the surface was underestimated by Lacroix. And that required the re-estimation of those parameters in our own work. And so that allowed us to further probe the differences between the different materials. Remember, the carbon black BP 2000 was the one with the high surface area. The V72 and the BP 120 are the ones with the more reduced surface area. The surface reaction rates are important for hydrogen production on all of the carbon catalysts, so irrespective of the surface area. Although we see and notice that I have used a logarithmic scale over here, so notice that the hydrogen production is way more pronounced on the BP 2000 as compared to the other ones. Looking at the methyl radicals, there we see that on the methyl radical is consumed on the BP 2000, which has a large surface area, but that, just like hydrogen radicals, it is also produced on the low surface area catalysts. Methane, on the other hand, is then produced on the surface of the high surface area catalyst, while it is consumed on the surface of the low surface area catalysts. This may seem slightly counterintuitive, that methane is getting produced here on the catalyst surface. Well, but what one will see, or what you will see, is that given the large production of the hydrogen radicals on the surface in the case of the BP2000. That is that the methane consumption in the gas phase in the presence of the large surface area carbon, that the methane consumption there will be way higher than the production on the surface. So that is essentially what one can observe here. So methane is indeed effectively also consumed here, and it is way more consumed in the gas phase in the presence of the BP2000 than on the other ones. So what we can also clearly see here is that the hydrogen radicals that were produced on the gas phase, on the catalyst surface, are reacting in the gas phase mainly with methane in order to produce hydrogen and a methyl radical. But the methyl radical is behaving differently. It is produced in the gas phase in the presence of carbon with a large surface area, and it is consumed on the low surface area carbon materials. Methane is getting consumed exclusively. Such an analysis of which reactions contribute to the overall conversions can also be captured in a figure as it is indicated over here. But in view of time, I will not discuss this in detail. If interested in the details, I refer you to Soroush's work, which was published last year. And looking further into the actual hydrogen production, what the different carbon catalysts mean with respect to hydrogen production, then in fact what is most striking is that for the blue catalyst, which is the BP2000, so the one with the large surface area, is that there with a lower temperature we can reach already a higher hydrogen outlet molar fraction. So a high surface area is really beneficial for the production of hydrogen. Okay, that brings me to the second part of the presentation, which is that on the reactor part and the reason to go for electrification and more particularly an electrothermal fluidized bed reactor. Many reactions in the chemical industry are endothermic, not to say strongly exothermic, and the reactors that have been constructed so far in order to perform those reactions have mainly been determined, the design of those reactors has mainly been determined by the heat transport. So narrow tubes, relatively narrow tubes, are being used within a fired furnace. And you can almost feel the heat from the figure which is shown here. But you can imagine that because of the endothermic reaction occurring within the tubes that are situated here, there can be a huge temperature difference, or a huge temperature difference will develop between the furnace and the inside of the tube, meaning that the heat is in fact not used at its best efficiency. So schematically represented, we have the situation as it occurs here. So we have a tube which is suspended in a furnace. So we have a very high temperature over here in order to reach, well, the minimally required temperature in the center of the tube. And those gradients, they play over a distance of, a meter, or the order of magnitude of 1 meter when it refers to the furnace. And of centimeters up to 10-20 centimeter when it comes to the reactor tube, so the place where the actual reaction is taking place. Now, being as a chemical engineer, we want to do better. We want to enhance the chemical reactions. Now, in this case, enhancing the chemical reaction is or can be done, or the manner in which we are trying to enhance it is by making use of electricity. And quite often, when we're talking about chemistry and chemical reactions, the comparison with cooking is made, and that is also what I will do here. So here you see an example of making some soup when going camping, and there is nothing else than some wood which you can set on fire in order to heat up the contents of the pot. But I think you agree with me that it's quite clear that quite a lot of the heat which is generated by by burning the wood is just getting lost in the environment. So we can try to improve that by containing the heat. So rather than having an open fire, we can close it into a stove, into a furnace. But still, the stove like this will not only be heating the food, you can almost also use it to heat the room in which the furnace is situated. And there is the chimney through which the flue gases escape, also still containing quite a lot of heat. So how can we do even better than just containing the heat? Well, by electrifying. And the way we do the electrification here is by heating the bottom plate on which the pot is being put, such that the heat is generated and by conduction and convection it can heat the content of the pot. But can't we even do better than that? Because in fact, we're still doing the kind of same thing. We are heating from outside, and then by conduction and convection, we bring the heat inside. Well, thanks to the use of electricity, there are indeed opportunities to do better. And then we can think of microwave or of induction plates, which still partly bring the heat from below, but by having some salty water, making some salt in the soup, also the fluid in the pot will be heated directly by the alternating magnetic field. Still, I think everyone also has experienced some challenges in heating the content of the food which is in the microwave. So it's not necessarily a straightforward solution, but heating from the inside is the out-of-the-box thinking, which allows also the intensification of quite some chemical reactions. And this then brings the limiting factors from the meter and the centimeter scale. It brings them to the millimeter scale on which of the catalyst particles, where the heat is being generated thanks to the electricity. And so now the transport of the heat is no longer a limiting factor, but the limiting factor will become the transport of the reagents into the system, into the catalyst. Okay, there are different types of electrical heating possible, induction, microwave, Joule heating, even there is sonication and plasma. Now, without dwelling too much on that, the Joule heating is the more conventional among all those, and the one from which we consider that it more brings the heat where we really want it to be. So we have chosen for Joule heating in combination with an electrothermal fluidized bed reactor, from which you can see a picture in operation here. So there are carbon particles being down there. There is an electrical potential generated between the electrode, the central electrode, which you can see being dipped in the bed, and the outer wall, which is acting as the second electrode. It is a relatively low voltage. It's in the order of 10 to 20 volt, which allows generating the high temperatures such that you can see the glow as you see it over here. So compared to conventional fluidized beds, by generating the heat in situ, we have a better control over the bed temperature. It's a highly energy efficient methodology, and it is rapid. It results in rapid and uniform heating. So TNMEC is a Ukrainian company which holds the IP on this type of reactor. originally being employed for solid carbon production of high quality, now also in view for the use for chemical reactions and hydrogen production. So how does the fluidization combine with Joule heating? The fluidization is in the bubbling regime, so it is not that vigorous, meaning that there will always be direct contacts between catalyst particles and the electrodes to have the current flowing, and the material which is contained in it, which should be partly conductive, of course, but also partly resistive in order to generate the heat, such that electricity can run and produce heat, and these are the results of some thermal demonstration of how the bed resistivity, for example, has evolved over time. And after some initial breaking in period, you see that the bed resistivity is working in a quite proper manner. And these are some actual time measurements where you see that, there are the fluctuations because of the bubbling, but there is as such a quite steady operation. So one of the challenges is to turn such a true reactor, such an ideal reactor, to turn it into mathematical equations. And in order to do so, we have on the one hand a mass balance, which considers the bubbling by considering a low density phase and a high density phase. So there is the convection, the reaction, diffusion, and then the transfer between phases. The main difference between the high density and the low density phase will be the extent of diffusion, the extent of mixing, which will be more pronounced in the high density phase as compared to the low density phase. For the heat balance, there is again a convection term now complemented by a conduction term, the heat of reaction, and then the heat generation because of the Joule heating. And this is the innovative term also in terms of the reactor modeling that requires the calculation of an electrical field. And this is effectively what Klaus has been doing in order to be able to come to a model of a reasonable complexity. So this being the detailed representation of the ETFB reactor, we can make it cylindrically uniform, or cylindrically apply cylindrical symmetry, such that we in fact just need to consider such a slice on which we can in the first instance solve the Laplacian field expression, which is a complex expression taking a significant computational time. And analyzing the results of this Laplacian field model, in fact, we can divide what is happening in two zones, namely a coaxial resistor zone where the bulk of the heat is being generated, and a truncated cone resistor for the part of the current which goes to the bottom, in the assumption that the bottom plate is also conducting, so that the outer electrode in fact is the combination of the bottom and the wall. In newer calculations, we have no longer considered the bottom plate to be of a conductive material, such that the two electrodes were the central one on the one hand and the outer one on the other hand. Fine. So the ETFB reactor model is like that, reduced to a simple model. And this figure compares the difference in simulation results between the Laplacian field model and the truncated cone and the coaxial resistor and truncated cone resistor. So as a function of the relative electrode width, so how wide the electrode is compared to the diameter of the reactor, and on how deep the electrode is submerged. So, and here you see that for quite reasonable combinations of submersion depth and width, that the simplified model is effectively performing well. And this is also evident from a thermal model validation. You see how this on the left-hand side is the validation for the Laplacian field model. So for the detailed model, there we can capture all data properly. Only in case that we are making use of the simplified model, the current partitioning model, the simplified one, then in the case of a submersion of 25 millimeters and not that deep yet, we see a somewhat more pronounced deviation. But for the more realistic ones that we want to use, the model can be considered as being validated. And hence, we can then also use it in order to do upscaled simulations. These are among the most recent simulations which we have done, and where you see on the one hand the temperature as a function of the length of the reactor, and you see the further evolution of the methane conversion. So what is quite noteworthy here is that in the red and definitely in the purple, we are reaching quite high conversions, and you see that particularly for the purple one, once full conversion is being reached, the temperature in fact further shoots up to undesiredly high temperatures. So reaching the desired conversion will be a matter of proper control, because on the one hand, of course, we want to reach full conversion in order to have the maximum performance of the reactor, but we should also ensure that we do not reach full conversion too early, because otherwise the temperature, there may be undesired temperature excursions. And well, the proof of the pudding is in the eating. This is the reactor setup that has now been installed, and for which there will be an opening event on Thursday. So it will also be nice to see you all over there. And the reactor that we have been simulating computationally, well, this is how it will look like. And we are looking forward, of course, to apply the model to data that will have been generated in that reactor by ourselves. So coming to conclusions and perspectives, well, by the work we are doing, we are putting the electricity in the catalyst, meaning realizing that reactor electrification is not just connecting an electric heater to the grid, but by bringing the electricity where it needs to be in order to deliver the desired heat. An electrothermal fluidized bed reactor was the reactor of choice for us because of the opportunities it brings to perform endothermic reactors. We focused on methane pyrolysis as a reaction, and what we understood is the crucial role of the surface area of carbon materials. It enhances the hydrogen radical formation and resultingly the methyl radical formation in the gas phase. And it leads to higher hydrogen purities already at lower temperatures, such that we can work more efficiently with a higher efficiency. Nevertheless, with time, I did not really elaborate on that in detail, but with time and catalyst deactivation, carbon deposition occurring, slightly higher temperatures or higher spacetimes are required to compensate for the deactivation. Finally, the ETFB reactor, we crucially simulated the impact of the electrode submersion depth, which enhances the heat generation, and we should properly take care of temperature excursions in case of full conversions. So what remains is to thank Interreg and particularly the combination of the regions France, North of France, Wallonie, Flanders for generously supporting us via the OBIWAN project. And of course, our collaborators, and more particularly Surush, Klaus, and also Simon, who is not listed here yet, for all their contributions to this present work. And of course, I also thank you for your kind attention.
Our second guest speaker today is Alexis Paletta from Université d'Artois, whose research expertise lies in green chemistry and biomass valorization. He obtained a PhD focused on sustainable chemical processes, covering the full value chain of biomass utilization, from extraction to molecular characterization of bio-based extracts, including the evaluation of their biological activities. His doctoral work also addressed enzymatic modification of molecules, as well as the modification of polymers using environmentally friendly processes. As a research fellow at Université d'Artois, Alexis is currently working on the VALCELMAT project, in which he is responsible for both the scientific coordination and the project management aspects of research activities dedicated to cellulose modification. He will introduce you to the VALCELMAT project and give a guest lecture on challenges and context of cellulose valorization, functionalization to produce high-performance materials. Alexis, the floor is yours.
Thank you again, Elizabeth, for the kind introduction. Today, I'm going to talk to you about the VALCELMAT project, some challenging and context of cellulose valorization. And so, here you have some names on scientific coordinator of the project, like Nicolas Joly, Karen de Klerk, Sophie Dropsik, Sabine Gosselin, Jonas Fonory, and Patrick Martin. Obviously, we are more people in the project, and I see some participants in this video meeting, guest speakers who are involved in the project. So first, some elements of context of the VALCELMAT project. The objective in Euro is to reduce the net greenhouse gas emission by at least 35% by 2030. We want to reach carbon neutrality by 2050. But obviously, I think every people know we have petroleum-based products in all the areas of the society: packaging, textile, insulation materials, additive for biopolymers, and we have, as consequences, environmental impact. So we need to find alternatives with an abundant biomass using green chemistry processes. It seems quite easy as objective that we can start with the short history of the cup, this plastic cup. When you think about this plastic cup, you think about, for example, birthday party, coffee room at the university, because we use it all the days. And in the last year, we find an alternative with this paper cup. It seems to be a good alternative. We can take a fresh coffee with this paper cup, and we use it for orange juice, soda, coffee, hot water. But the reverse phase of this paper cup is the fact that, okay, it's bio-based, but we have plastic in this product. In fact, to have good property, good bio property, we have a coating and plastic film inside of the cup. And so it's a kind of reverse phase of using bio-based products. We always need plastics to have a good property. And it's the same challenges in food packaging. For example, when you go to buy a pizza or French fries, you need to have a packaging to have a property to against the oil, an oil barrier, water barrier. And so it's quite difficult to use only bio-based products today. It's the same for textile. My question went well if we should be in a room, a real room, but here we have one question: who doesn't have at least one piece of clothing made with synthetic oil-based fibers? I think all the audience have at least oil-based fibers in their clothes. So we have mixed fibers in the textile, and we have some problematic in the society, like fast consumption of textiles. So we need alternatives to face against environmental problems, ecological and social challenges with textiles. And it's the same things for technical textiles. And we think about clothes again, the rain, again the water. We have always hazardous substance in the textiles to answer some property like the water. Same things for composites, because it's another thing on the project. We have worldwide application of composites today, and the composites offer excellent performance, but pose major challenges in terms of recyclability, environmental impacts, and waste management. Because composites, it's a mix of products, and obviously today we have fully of composites that are made of a part of bio-based products, biomass. We put biomass inside the composite, but on the other side, we have always resins, oil-based resins. We have always some fibers from petroleum-based materials. So it means that we have difficulty to recyclable the composites with this solution. So we have some legal framework in Europe for this 3 area of the project. For example, the Green Deal for packaging. The idea is to have by 2030 100% of recyclable packaging. So we can see, for example, for the paper cup, for the solution of the paper cup today, it's not the case. For textile, the strategy is to have textile without hazardous substance. And for the composites, it's not really a strategy, but the idea, at least in Europe, is to find is to use composites that can be less complex, and that we can reuse it, or at least have a good strategy for recyclability of composites. So the VALCELMAT project want to answer to this big question, this big problem, and the idea is to use the cellulose itself to have a good property, for example, for the paper cup. So we want to modify the cellulose, the most abundant biopolymers on Earth, modify it to have a new property, functionalization of cellulose, formulation of composites for free array, packaging, food packaging, materials, and bioplastic, for example, and textile, obviously. And the idea at the end of the project is to offer available products and processes at prototype pilot scale that can be transferred to manufacturers for all the free hours. So the VALCELMAT projects want to answer to social issues, safety, use, recyclability products, environmental issue, bio-based products, environmental compatibility, regardability of the product, and efficiency and economic challenges, high performance processes, low cost processes, and transferable to the industry. And so in the project, we have 5 partners, 5 operators that are involved. University of Arthur for the batch processes, characterization. We modify the cellulose. Materianova in Wallonia, in Mons, for the extrusion processes, continuous chemistry, and we exchange the processes to transfer the batch reaction into extrusion reaction. Then when we have good materials, we have the UPJV, University of Picardie-Jules Verne in Amiens, that test the biological property of the materials, the degradability of the new cellulose, and the production of microbial cellulose 2. And on the other side, we have UGent and OGENS in Flandre for the textile application, spinning, electrospinning, coating of all the materials. Obviously, we have 8 associated partners In the project, Aura Materials, Bioeconomy for Change, Plastium, Valbium, Plastiwin, Greenwin, Fedustria, and Artevelde Hogeschool. And we are working with these associated partners and industrial to find the targets of the society in order to are in phase with the solution that we can propose during the project. So after this some slides about the context and introduction, I will switch on scientific activity of the project with only two parts because we have other subjects in the project, but today my talk will focus only on hydrophobization, effication of the cellulose, and inifugation and fireproofing of cellulose. And so first, the part of hydrophobization. So we try to obtain phases, so it means fatty acyl cellulose esters. The first step is find a good way to solubilize the cellulose. So for the moment, we use a not completely green solution, but it runs well with the solution of lithium chloride and dimethylascamide to solubilize the cellulose. And then we are able to esterify the cellulose using fatty acid chloride. And so we can control the substitution degree. So the substitution degree means the number of hydroxyl that we can esterify on the units of glucose of the cellulose. And so by controlling the equivalence of fatty chain, we can control the substitution degrees in the materials. And so we can play on this equivalent to obtain various materials. So we try it with various length of the chain from C8 to C16. And so then after that, we can cast the materials, the ester of cellulose, to obtain like a plastic film, you can say like this. And then with this plastic film, we can perform some analysis. So we perform hydrophobicity analysis, resistance in some condition, to acids and alkalis, mechanical property, thermal property, structural analysis, and solubility of this plastic film. And obviously, we can play on the quantity of phase, so we can obtain we can play on the high density of the films, and so we can have various applications for these plastic films. So here we have some, you can find some results about the analysis that we perform in the lab in University of Artois. For example, for the hydrophobicity of the materials. So we can see that we have in all cases for the faces, we have hydrophobic materials because we have higher angle of contact for this material. So it means that we have hydrophobic materials. We have performed some analysis in strong condition like sulfuric acid, for example, and we have no significant change. So it means that the bioplastic can resist to a strong condition. And then we study the structure by infrared spectrum and NMR spectroscopy. If we look at the mechanical property of the film, we perform some mechanical analysis, and we can see that the transist rates tend to decrease with the augmentation of the carbon. So it means that when we have a long change, we have a transist rates that decrease, but we have no clear evolution of the yield stress in this mechanical property. If we look at, for example, here the Young modulus analysis, we can see that for the faces we are near the in comparison to a low density polyethylene plastic. So it means for the part of the hydrophobization and esterification of cellulose, we are able to obtain some phases, fatty acid cellulose ester, that are hydrophobic plastics. And in the project, we try to proceed to make these faces in conventional plastic processing method. And currently, we're trying to make extrusion with Materia Nova for this part of the project. And the mechanical properties are near due to the low density polyethylene plastic. We are currently working on the application of this bioplastic, trying to use it in composite, for example, in a fully bio-based composite. We are trying to use it in food packaging and in biomedical composites to replace some plastic. And obviously, we are testing this plastic at UPGV with the colleague from Amiens on the biodegradability of these materials and on the microbial property, antimicrobial property. And for Jugend and Jugend, we are trying to see if you can make a textile, if you can spin by electrospinning the materials. In parallel, we are trying to add additional property to increase the potential of this bioplastic by the addition of biomolecules, a bio-based additive, during the casting in the plastic films. So we are trying with some bio-based additive at low quantity, 0.1% of weights by volume during the casting. And we have done recently some thermogravimetric analysis and antioxidant activity in solid phase for these new films. And it's quite nice for the moment, but I invite you to follow the project to have the results in the future. The next step of my talk will focus on inifugation and fireproofing of the cellulose. So it's a Materia Nova part of the project. So in Materia Nova, Sophie Ropsit team tried to make reaction using ball milling processing. So the idea is to phosphorylate the microcrystalline cellulose to have resistance or at least a property of flame retardance. So why we use ball milling in this part of the project? Because it's a solvented process. So it's a green processes, and we have a good reactivity of the cellulose in ball milling because we have a mechanical activation that enhances cellulose activity, and it means faster reaction and effective phosphate group grafting on the cellulose. So the first steps here was to graft P2O5 on the cellulose. So in the project we test various balance of P2O5 in the reaction, and we can follow first the color change and the structure change of the microcrystalline cellulose. But on the second step, we can follow the grafts of the P2O5 by ECP on the microcrystalline cellulose. So here some results, for example, for the third condition with a higher quantity of P2O5 at the beginning of the reaction, we can reach 17% of phosphor content in the materials, and so a degree of 2 on the cellulose. So it's quite high substitution degree, and it's correlated by infrared spectrum analysis. In fact, for the first and second one materials with a low quantity of P2O5, we don't see a significant change in the infrared spectrum. Instead, for the third one, we can see a big difference in the spectrum, similar to a graphitic structure. Then the idea was to put it in a composite. So the microcrystalline phosphorylated cellulose was put into a polypropylene to obtain a composite with various ratio of polypropylene and microcrystalline phosphorylated cellulose. And so the the property as a flame retardant was evaluated. And so we can see here that for the blue one, it's the polypropylene, the initial polypropylene. So we don't have a flame retardant effect for the polypropylene. For the third one here, the microcrystalline phosphorylated cellulose with the higher content of P2O5 or phosphor, we can see that we have a good retardant effect, flame retardant effect. So it means that this composite is probably a good solution to have a composite that have a flame retardant effect. Then the property, the mechanical property of the composite was evaluated in this part of the project. And we can see here the polypropylene in black one. And for the blue one, that was the better one, we as flame retardant effect, we have at least, it seems to have effects that are near to polypropylene ones. So we can conserve the ductile behavior of polypropylene with the flame retardant effect. So it's an interesting thing. And you can find this research in the article that are here published last year during the project. For the application of this phosphorylated polypropylene microcrystalline composites, it can be in aeronautics, aerospace, for various structures, because in this application area, we have strict fire safety requirements. It can be automotive for dashboard insulation, battery in electric vehicle. At this moment, I think it's quite interesting property. In construction, civil engineering, in textiles, and phosphorylated cellulose, it is currently testing with in textile application. For packaging, for example, if you want to transport some elements like, I don't know, a smartphone or something like this that are battery, we can use packaging with flame retardants. So next, I'm near to the conclusion. We are currently testing various things in the project, trying to make eco-efficient chemistry with industry available processes. And for the hydrophobization of cellulose, we are trying to have a greener process with another solvent that we are currently developing in the lab. And we are trying to draft some other compounds to improve the characteristic and the property of the plastic films. If you want to follow the project, I invite you to snap this QR code to the website of the VALCELMAT project. We have a newsletter, an active newsletter, and we are trying to make some vulgarized article every 6 months to keep the information with the people. And to discover the latest development of the project, I invite you to follow us on LinkedIn. We are very active on LinkedIn, and probably we can take internship during the next year. So if you have students available for internship, we are available to take it as intern. And that's all from me. Thank you for your kind attention.
Our third and final guest speaker today is Maxence Renaud from IMT North Europe. Maxence is a materials engineer with a strong background in microwave processing and additive manufacturing of ceramics. He obtained his PhD at the Ceramats laboratory of the Université Polytechnique Hauts-de-France. Alongside his academic work, he began exploring 3D printing since 2018 for personal projects and progressively integrated additive manufacturing into his research activities. He joined IMT North Europe for the first time in 2022 and returned in 2024 after an intermediate employment at the R&D department of the startup 4D Pioneers. He is currently working on the COMPOVERT project, focusing on the development of natural fiber reinforced composite materials, to which he will give you an introduction as well as a lecture on additive manufacturing at the service of R&D. So Maxence, the floor is yours.
So thanks for Elizabeth and all OBIWAN and VALCELMAT committee to ask me to make this guest lecture. I will present you something a little bit different than previous with the application of additive manufacturing at the services of R&D. I will speak with the COMPOVERT project. I will present this project later in the presentation. So, as Elizabeth said, I'm a doctor engineer and I'm a postdoctoral researcher in IMT Europe, previously called Mine de Douai. So, I will try to explain you how additive manufacturing and, for example, low-cost additive manufacturing could represent a good opportunity for R&D in lab or for industrial. A little bit of context. This is a graph with a 3D printing market, and we could see that between 2020 and 2026, the market is growing up by 3, even in industrial or R&D services or in consumer and large public. So that it proves that additive manufacturing could represent a good opportunity to change the way to design a product, to make another product. So it could be interesting to join additive manufacturing and use case in research or industrial. Just to the summary, I will explain you some fundamentals of additive manufacturing. After I show you additive manufacturing in action, presenting you some prototyping and some realization in IMT Europe or, for example, in my previous job, and with another Interreg project called Agility. After, I will present you the Interreg project COMPOVERT and the application with additive manufacturing. And after, we conclude and if you have some question. First fundamental of additive manufacturing. Let's defining additive manufacturing according to the standard. Additive manufacturing is the process of joining material to make some parts in 3D from 3D printed data. Usually layer upon layer, opposite to subtractive manufacturing and non-formative additive manufacturing technology. In the picture, we could see an illustration of this difference. On the left, we have additive manufacturing with powder bed fusion. I will explain after. Opposite to the right with subtractive manufacturing. On the left, we could create this gear from powder without using a very big block of material. Opposite with subtractive manufacturing, when we have to use a big square of stainless steel, for example, and use CNC machining, milling, drilling to have the final gear, it generates a lot of waste and a lot of time. So additive manufacturing could represent a very, very good opportunity to make to change the design of the object, to change the way to produce some object. Now the spectrum of technology. I will not explain all the technology, but in the standard there is 7 kind of additive manufacturing technology. That polymerization with a source of light which will photopolymerize liquid resin, which commonly is one of the most precise technology in additive manufacturing. Second, material extrusion, I think is one of the most used technology for R&D or for market, very common people. After we could have material jetting, binder jetting, powder bed fusion with polymer or metal, which is very interested for R&D in lab and for industrial. Direct energy deposition, we could be very interesting, and after sheet lamination. So what are the advantages and disadvantages of additive manufacturing? First, the advantages, we can see with this illustration that with additive manufacturing, we could have very complex geometry, which are very impossible with CNC machining. For example, we can observe this jet engine. It's not possible to CNC machining the inside of the engine. Another example for medical application with bespoke implants, we could reduce the time of the operation of the patient by using 3D printing, by preparing in amount the piece that we need to, for example, repair the crane. Prototyping and lead time. We could enhance the iteration, the speed of the iteration, that we could, thanks with that, we could have more agility and efficiency in producing some objects, in particular some prototype, and sustainability, thanks to the using of only the amount that we need. Sometimes there is some support for helping the additive manufacturing, but contrary to CNC machining, we don't have a lot of flex due to the machining process. Some disadvantages and challenges of additive manufacturing. We could have a roughness of the surface due to the stair-stepping effect. It's a process which could be quite slow regarding to traditional process, for example, injection molding, which we can have pieces in 1 minute, contrary to additive manufacturing in 1 hour, for example. The feedstock cost, because you have to transform the raw materials to adapt to the additive manufacturing technology, it could be more expensive than common technology. And one of the disadvantages is the anisotropy ratio. We don't have exactly the same properties in all the axes, along the axes, that it could be complex to use in industry, for example. This is a more precise table, for example, so I will not explain all the line. It will resume on the previous table. So now what is the material landscape of the additive manufacturing? We could print polymers with PLA, ABS for prototyping, high performance material for PEEK polyether ketone, PE, PPS, or resin. In metal, we have a large range of metal, copper, steel, different steel, titanium. For ceramic, we could print zirconia, alumina, refractory, technical alumina, and bioceramic, triphosphate calcic or hydroxyapatite, and there is a lot of application with, for example, food, human tissue, and concrete. For example, in next to Valenciennes in France, there is a society called Machine 3D, which is one of the most the highest building in 3D printing in Europe, I think. So now I will present you some study case and application of additive manufacturing that I could make in the lab of my job or my previous job. So rapid prototyping in lab. For example, after my PhD, I use microwave to make some sintering of ceramics, and we have to control the temperature. So I designed a support and holder for infrared camera. And the advantages is that I could produce this prototype in PLA, which is very cheap. I only need 3D iteration to adapt the dimension, the size, and it printed with my own Creality. It's a low-cost 3D printer. So, for example, in the lab, a 3D printer is not a very expensive investment. So it could be very useful to have a 3D printer in the lab. Another example in IMT Nord Europe, Becher holder for a PhD student in the black parts. She have a problem with temperature and pressure and the organic solvent inside the beaker. So we have to design a beaker holder which could be resist, and we print in PPSCS, polypolysulfone carbon fiber. And with this material, the holder could resist to all these constraints. And for example, other realization in IMT Nord Europe, in resin, we have produced high temperature and textured plate for vacuum fouling with a professor in the IMT Nord Europe. We produce demonstrator with copper, stainless steel, zirconia, and polyamide with carbon fiber. We printed demonstrator in bronze, for example, and a big tubular heat exchanger for another PhD student with ozone. And now, just let me make a small parenthesis to present you another Interreg project called Agility, where the aim is to supporting company becoming more agile thanks to 3D printing, which is linked a little bit with COMPOVERT. And we have realized demonstrator for this project. Thanks to 3D printing, we make the tool to make some objects. We could be industrial study case, for example. And one of the first demonstrator is injection molding. One of our collaborator is a musician and have a problem with the holder, the table for the partition, due to the breaking next to the bolt. So we decided to make a new design of this part, and the objective is to make by injection molding and to concept the mold by 3D printing and to produce around 40 parts of this object. We start the drawing of the prototype. We print the prototype in PLA to be very efficient and to test if the dimensions are good. Third, we print the mold with a resin, high temperature resin, and after we inject polypropylene with manual injection, and we can produce around 40 pieces. And the strongness of the additive manufacturing, that if we need to change something, we could very happily change and restart the cycle with the drawing, prototyping, print the mold, and etc. And for this object, we make 3D design that it shows that with 3D printing, we can gain efficiently, agility, and we can have customization. The first design is good, but there is another project with the breaking as a bolt on the top of the piece. So that is why we tinkering the bolt. But another problem in when we restart the injection, and the injection, the mold is overheating. So we can add conformal cooling inside the part and make water circulation inside the mold to refresh and to produce more than 40 pieces without problem. So this is the first example of how additive manufacturing could really help industrial or R&D department. Another demonstrator in the link to the COMPOVERT project and agility project. We want to produce a GSM case to have the phone protection, and we want to add some properties with dust protection and antibacterial protection. We concept the mold and we make injection simulation to adapt the mold and to see where the point of injection are the best placed. We make the mold by additive manufacturing. It's a big mold and we have amovible parts. And after we inject the mold with a polymer, with a biocomposite made in COMPOVERT with PLA and 5% amount of linen to have antibacterial and dust protection. And after we engrave the GSM case with a laser. Another study case is to make some mold with metal and with FFF. For example, we print a mold on the left with copper filament, which it's a filament which around 19% in weight of copper. The rest is thermopolymer. So we can print. After we have a step of debinding to remove the polymer, and after the sintering to consolidate the matter and weld all particle copper together. This additive manufacturing technique with metal, here you can see in copper, but we can have stainless steel, tool steel, something else, and it could be also applied with ceramic. So it's very low-cost way to have metallic or ceramic parts in a lab or in industrial. It is possible. I give small explanation. Thanks to the formulation of the polymer, we have powder mixed with backbone and a binder, and we could shape with 3D printer, filament or pellets. And after we remove the backbone, one of binder. Here is soluble binder, but could be a thermal removal binder. After this step, we remove the cohesion of the piece. So we don't have the final mechanical properties. That is why we have to heat the piece to activate the diffusion mechanism with temperature and to have the sintering of the matter to obtain a very solid metallic or ceramic pieces in the end, as explained in the bottom of the slide, with stainless steel spool printed on a low-cost device, sinter in an oven, tubular oven with a protective atmosphere, and in the end we could have gears or engine in stainless steel. Another example of my previous job is a project. It's called Fabio, with UCCS in Lille, and the objective of the project is improve the methanation reaction to valorize carbon dioxide and hydrogen by producing biomethane without filtrating the CO2 carbon dioxide from methanization, which is a very costful step. That is why we decided to use a structured metallic 3D printed reactor to have the controls of the temperature of the reaction and to improve the exchanges between hydrogen and carbon dioxide. And the idea is to put a new catalyst on the surface of the 3D printed reactor to improve the reaction and improve the selectivity according to the CO2. And for example, I can't give a lot of information because there is a lot of confidential information, but one of the methodology is to print, for example, with copper, a structured reactor with all the steps that I previously described, with the printed part, the binding part, and sintered part. And we can adjust the infill structure to improve the exchange between the gas and the catalyst on the surface. And thanks to this process and the roughness of additive manufacturing, it could be good to fix the catalyst on the surface to use the roughness to stack the catalyst on the surface of the reactor. Now, I will speak about the Interreg project COMPOVERT and the application with additive manufacturing. The COMPOVERT project, it's a project with the cross-border development of natural fiber reinforcement functional composite with valorization of local byproducts. It's a project, the consortium is made with CERTEC, University of France, University of Liège-en-Blou, the CRIT Materiaux Innovation and IMT Europe, and with associated partners with Albion, Greenwind, Bioeconomy for Change, and VKC. The COMPOVERT project, the aim is to develop eco-design functional biocomposite by upcycling local natural fiber using some standard or innovative process to shape the matter. For example, 3D printing or injection molding with smart and recyclable materials with advanced properties, antibacterial, antiseptic, antioxidant, for new regional industrial application. The aim is to create some biocomposite with a thermoplastic matrix, for example, polyethylene, polypropylene, or PLA. Use fiber particle, for example, composite with particle, flax, jute or starch, or continuous fiber, and to use innovative process to have a large scope of application to use this biocomposite. This is a kind of example of the process with additive manufacturing. For the moment, the Université de Reims and Université de Liège and CERTEC make a compound with a different amount of, for example, linen and a different thermoplastic matrix. And the aim is to use, for example, additive manufacturing to make some demonstrator. So with the pellet that all the partners made, we could make some spool to print with a filament 3D printer We've adapted some parameters, speed, temperature of a retraction process. And we could print some objects that we have to define regarding to the application that we go. Or we can use directly the palette with a 3D printer palette to print also some demonstrator. And the last part of the COMPOVERT project is to use continuous fiber to make some object demonstrator with natural fiber, which is very complicated subject because natural fiber is not very very have the same properties from the beginning to the end of the spool, is very irregular, so and have moisture inside the spool, so it could be very complicated. For the picture on the bottom of the presentation, it's carbon fiber or glass fiber. There is not a lot of device that we could print some continuous fiber. Is very complex. That is why the next step of the project COMPOVERT is to try to, for example, make a new device to print continuous fiber, or to find a device adapted and print with continuous fiber to have the special property of biocomposite. Now I will conclude my presentation, and if you have some question. For the conclusion, additive manufacturing is a real advantage in R&D due to the rapidity, efficiency, the customization. We could quickly change dimension, try again, and make some prototype in less than a day or a week. It's a low-cost process depending on the technology used. For example, FFF machines, filament machine, now could cost less than 2,000 euros. We could have also a piece in house making without you send the matter in society to make the parts. We could make inside. There is a large panel of materials and possibility. As shown in the presentation, we could make the final piece, we could make tools to make some piece, we could make in metal, ceramic, polymers, thermoplastic polymer, or resin, or composite. So there is a lot of application and possibility, and also in the design of the piece, we could use the additive manufacturing possibility to change the way to design a piece. And in particular in COMPOVERT, we will print some demonstrator with properties with the formulated biocomposite, anti-static, antibacterial, and we could use particle, short fiber, or continuous fiber.
And to end, I would like to thank Joris, Alexis, and Maxence for their interesting presentations, and all of you for participating to these guest lectures. I would like to acknowledge the funding which we all received from the European Regional Development Fund via the Interreg France-Wallonie-Vlaanderen program, together with funding from our local authorities, being the province of East Flanders, Vlaio, and the Walloon region.